I'm sure you all remember that the gravitational force on an object of mass m near the surface of the Earth is mg. The gravitational force is really due to an entity called gravitational field. This field surrounds the Earth and in turns make any test mass, little m, put near the Earth feel a force, which we call the gravitational force. You probably also remember that little g did not depend on the mass of the object, little m. So that object could be used as a probe of Earth's gravity. Let's transfer the same line of reasoning to charges. Can you measure the influence of a charge on the space surrounding it? Analogously to the test mass, you could use a test charge. If you put a test charge Q0 at a point P, it will feel a force proportional to the strength of the electric field at that point. In this sketch, we have assumed that the test charge has the same sign as the charge Q, so it's repelled by it. If you repeated the experience with different test charges, you would notice that the force would be proportional to the test charge, just as the gravitational force of the Earth on a brick would be proportional to the mass of the brick. But the electric field should be the same regardless of the presence of a test charge, because it was solely generated by charge Q, just like the gravitational field probed by the brick was generated solely by the Earth. Since Q is no special charge and all charges generate an electric field, the assumption here is that the electric field generated by the test charge is incommensurably smaller than the one generated by charge Q, just like the gravitational field generated by a brick is incommensurably smaller than that generated by the Earth. So to make the measurement independent of the particular choice of the test charge, we could take that force and divide it by the value of the test charge. The same way we would find little g by taking the gravitational force on the brick and dividing it by the mass of the brick. This means that an electric field is an electric force per unit charge. The units are newtons per coulomb, and you need to keep in mind that in this definition, Q0 is a test charge that has to be chosen much smaller than the charge you want to measure the field of. Although the electric field's direction will not depend on the test charge, what the sign of the test charge determines is the direction of the force it feels. So, if in the same electric field you put a positive test charge and a negative test charge, they will feel forces in opposite directions. You can easily see that there is no contradiction, because if you flip the test charge Q0, you'll also flip the sign of the force F0, so the ratio F0 over Q0 will not change sign. So flipping the test charge has no effect whatsoever on the electric field you're trying to measure. But how do we really visualize this electric field? There is a clever method that was invented by Michael Faraday, that of drawing field lines. Although they are called field lines, they are actually curves. The tangent to the curve at any point reflects the direction of the electric field at that point. Here is an example. In a moment, you'll see that there is only one special case in which the field lines are straight lines. Here are the electric field lines for a point charge, which here is the sole source of field. Of course, the electric field occupies the whole three-dimensional space around the source, but this is just a slice using a plane that goes through the location of the source. For a positive source, the electric field lines point radially outward from the source. In fact, a test charge of positive sign would be repelled if placed anywhere around the source. Using Coulomb law and the definition of electric field, we can easily derive the expression of the electric field magnitude generated by this point charge. In this expression, Q is the source. If the source of the field is a negative point charge, then the field lines will point radially inward, because a positive test charge abandoned anywhere around this source would be attracted by it. If the absolute value of the charge is still Q, the expression of the electric field magnitude is of course the same as before. To recap, the strength of the electric field around an isolated point charge decreases with the square of the distance from the charge. What if instead of an isolated point charge, we have two point charges? Here is the case where the two charges have the same sign. The electric field is the superposition of the electric field generated by each positive charge, and it's very complicated to derive an expression for the electric field at any point around these two charges. However, we can make sense of these field lines. If a positive test charge was abandoned anywhere on the positive y-axis, it would be repelled by both positive sources and be expected to accelerate along the y-axis. If that same test charge was abandoned anywhere on the negative y-axis, it would accelerate in the negative y direction. However, if this charge was exactly at the origin of coordinates, the field produced by the left source would point in the positive x direction, and the field produced by the right source would point in the negative x direction. Since these two sources are equally far from this point, then the magnitude of their electric field would be the same. So these electric fields would be equal and opposite, and the net electric field would be zero. What if there are 2-point charges with opposite signs? This is called an electric dipole. It consists of a charge positive q and a charge negative q at a finite distance. The net electric field is again the superposition of the fields produced by the individual sources. The field lines look qualitatively very different in this case. We can make sense of them by pretending to put a test charge at some point. For example, if you put a positive test charge along the line between the positive and negative source, then that positive charge will be repelled by the plus q and attracted by the minus q, eventually sticking to the minus q charge. So if you are asked where is the electric field strength maximum, the answer would be the midpoint of the line joining plus q and minus q. For the same reasons as in the previous example, the magnitude of the electric field produced by the plus q and the minus q would be exactly the same at midpoint. That would be the point where the two field strengths will add up the most. Incidentally, an example of molecular electric dipole is a water molecule. Electric field lines plot are not to be read like some familiar maps. There is a number of cautions we need to take to avoid misinterpretations. These lines do not represent places where the electric field magnitude is the same. In fact, the electric field strength changes along these lines. In particular, it decreases every time you move away from a source and increases every time you move toward a source. It will be sufficient to remember E equals kq over r squared. Also, field lines are not like streamlines in a fluid. Test charges do not move along them, the only exception being when the field lines are straight. Electric field lines can never cross. In fact, the force the test charge is subject to would not be unique if there were two possible directions of electric field at a given point. That, of course, would make no sense. Since the direction of a force on a test charge is always along the same line as the electric field at that point, then it follows from Newton's second law that that's the direction of acceleration as well. Remember that the acceleration could be parallel or anti-parallel to the electric field depending on the sign of the test charge.